Up to this point, we've used Boolean algebra and shown how we can apply properties and identities of Boolean algebra to reduce logical expressions. And of course, I think that it's reasonably obvious that by reducing the number of terms and the number of variables that appear in those terms, you could actually implement an equivalent Boolean expression with a smaller, more efficient circuit. So that's the overall goal. And what I wanted to do today was show you the link between Boolean algebra simplification and what Karnaugh maps do. So I think the key is that Karnaugh maps show you what I call logical adjacency, where a couple of terms are sitting right next to each other, and you can apply Boolean algebra to make those terms reduce. So logical adjacency from Boolean algebra appears as physical adjacency on Karnaugh maps. So we'll talk more about that, but I wanted to show you the explicit Boolean expressions that show up whenever you look at a minimization problem. Okay, so let's take a look at this logic expression. This logic expression, we've talked about how this follows onto a Karnaugh map. Each one of these product terms is a square on the Karnaugh map. So I've got 4 ones showing up on this 8-square Karnaugh map, and I've got 4 product terms, one for each of the ones. Okay, so what I want to do next is I want to notice that these two are sitting right next to each other. I could have done these two, but these two are sitting right next to each other. So let's go to the next step. We can identify that this term in orange, those are the 2 ones here. And in purple, we have these 2 ones. And this corresponds to factoring the x bar z out of the first 2 terms. So if I look at this term and this term, x bar z, if I distribute that back through, that becomes these 2 expressions. Same thing over here for factoring out xz. So x and z are common to these 2 terms. You factor this out. And then you get this logical expression y or y bar, which we know from Boolean algebra properties, that simplifies to 1. All right, so immediately, because we had these adjacent squares that identified that, oh, this is only going to change in one variable. Because it only changes in one variable, that's the reason we use a gray code. Only one variable changes as we go across adjacent cells. All right, so that means that simplifies out. And we can go to the next step and notice, oh, these 2 groups of 2 are actually right next to each other. And so that, this is the simplification we have so far. But now I notice z will factor out of this. Okay, so z is common. And so that's my next step. That group of 2 could actually be considered a group of 4. And when you have a group of 4, you can do this process essentially twice. And you have x bar or x factoring out, and the final result is that we get just this logic expression simplifies to z. All right, and so I think if you notice in hindsight, that's reasonably obvious. This is the same region as z on a Karnaugh map. So I just wanted to show you this to surface exactly what's going on with the Boolean algebra that is that K-maps are motivated by Boolean algebra, and this shows how that link works.